So right now we're going to do is the formation of the alcohol from an alkene. When we work with alcohols, is it usually under acidic or basic conditions? Acidic. And so this one requires an acid once again, and it will follow Markovnikov's rule. And so just in general, just to have a generic reaction, we're going to have some alkene. And here, what do you suppose, if we're going to make, this is our ultimate goal, is to make an alcohol. Make an alcohol here on campus. What do you suppose that we're going to be adding across that bond? I mean, this is like, on Jeopardy sometimes they have like stupid answers as a category. This is like a stupid answer question.
An acid.
Close. Water. H-O-H. It's water. And so it is under acidic conditions, but it's just water. So there's the acid, and of course it takes a water. Okay, so plus water. All right, or sometimes they will even just put the water, comma, acid on the reaction arrow. They don't even put water down as a separate reactant, okay, for the way it's written. It is electrophilic condition, so let's just go ahead and work through the mechanism. I'm going to go ahead and just scroll this up so that way we can hopefully have more room. Yep. Okay, so we have an alkene, CH3, CH3. We have our acid. And I'm just going to do it generic, H3O plus, and it really would look like H3O plus since this is under aqueous conditions with water. So, but you could write it down as H2SO4. That's an acid that gets used a lot. It's H2SO4 here. It doesn't matter so much. Okay, what do we have here that's going to be similar to what we've already done in the past? It's electron rich that can go and do the attacking. The double bond. And now it's going to matter, this is an asymmetrical double bond, and so it's going to matter which direction it swings out. And so the double bond's going to swing out to attack something, and what will it swing out to attack? The hydrogen from the acid, because that's what acids do. What is the rule of thumb with respect to acids? When you see an acid, you protonate. Okay, and so we have two possible ways. We could have it swing out, attack the hydrogen where the hydrogen gets added to, I'm going to call this one carbon 1. Well, I'll say left carbon, or we could have it swing out and have the hydrogen added to the right carbon. And so is it going to be added to the left or the right? The left. According to Markovnikov's rule, it's going to be added to the left, because that's the one that's got the highest number of hydrogens directly attached to the double bond already. And so let's go ahead and we'll draw that in. So a lot of times I just draw it like where it looks like a little lever swinging out, boom, boom. Sound effects optional. Do you suppose, well here, let's draw what this is going to look like. And if you don't mind, since the methyl groups now, they don't do anything, I'm just going to draw them as MEs from here on out to make it more quick. And so always draw what didn't change. We have the Me attached to that carbon that already had one hydrogen on it. But now there's only one bond between the two carbons, and then we have the two methyl groups. We have the hydrogen that came from the acid, and we have water as the product. Okay, what am I missing, if anything, here? Pardon? What is missing? Right, the carbon on the right side has only 3 bonds, so therefore it is a... Someone said it, say it with some conviction. Carbocation. So And that's the reason why Markovnikov's rule is correct, because that's more stable than if the carbocation was on the other side. Whenever we form a carbocation, is that usually a fast step or a slow step? Slow. And so this is the slow step, or the rate limiting step, because carbocations are not happy. Okay, so hopefully I haven't lost anyone so far. We've got this carbocation. It's actually, so far, it's been pretty much the same as what we saw with the alkyl halide. It's just under different conditions here. And what do you suppose is going to happen next? Do we have anything that's electron rich that can go out and do the attacking? The oxygen. And so let's go ahead and do this. And what is electron deficient that it can attack? The carbocation. Boom, boom. Now, it may not be that exact same water molecule, because acids and water will be exchanging hydrogens constantly, but I've just drawn it in for clarity's sake here. Okay, do you suppose that this is going to be fast or slow? This one's fast, because it's not going to be happy to have the carbocation, so it's going to want to get rid of it. So now we just draw everything that did not change. We have the left carbon with the methyl, hydrogen, methyl, methyl, HO. And I'm not skipping any steps right now. Please note the oxygen is positively charged. I am going to try to scroll this up a little bit so that way we have more room. Okay. And by we, I mean me. We're not quite ready. Technically, right now we have an alkyl oxonium ion. Alkyl because it just, carbons and hydrogens. Oxonium is the positively charged oxygen. And so what do you suppose is the last step? If this is acid catalyzed, we must get our acid back. And so how can we get our acid back? What? If you look back, I can't show you because I've already scrolled up, but if you look back in your notes, what have we not used yet? No. Someone said it. Water. Because remember, it was the alkene plus a water. Well, we haven't plus the water yet. So what do you suppose is going to be coming in doing the attacking now? It's a water molecule. I'm just going to do it in this color because we've got to get our acid back since it's acid catalyzed. And so this water is going to attack what? One of the hydrogens off the oxonium ion. Boom, boom. Sound effects optional once again. Do you suppose that this is fast or slow? This one's fast. Is it going to be reversible or irreversible? It's actually reversible because, like I said, alcohols and acids in water, they all just kind of, they're swingers in the sense that they have what's called proton exchange. So they're constantly swapping partners. One hydrogen is just as good as another hydrogen for the most part there. That is not faith integration. So I'm going to scroll this up a little bit more so that way I have more room to write. And so, like I said, it's going to be reversible, it's going to be fast, and I'll try to keep my colors the same. This time I'll put the CH3s, draw everything completely out. CH3, CH3. This one's really... Whoops, I already lied and changed my color, but hopefully that's all right. Okay, and then technically we did get our acid back. So, H3O+. I would expect you to be able to name this product because it's just an alcohol. So how many carbons are in the longest carbon-containing chain that has the alcohol in it? It's 4. So its root will be butanol. Okay, so we have to, let me scroll everything up a little bit so I can write. So its root will be butanol. And, of course, so what number will the will the alcohol be on? And so I heard two different things, and actually I can't see it because, let me just double check. And so it's going to be hanging off of carbon number 2. Okay, so because it's going to be 1, 2, 3, 4, so it's going to be a 2-butanol. And then we have to name the other functional group, which is a 2-methyl. Okay, so let me go ahead and type that out. So it is 2-methyl 2-butanol. There we go. Okay. So now we have a way to go from an alkene to an alcohol. We have ways to go from alkenes to alkyl halides. We also have ways to go from alkane to an alkyl halide through free radical halogenation. There's a section in this chapter that's just a review of thermodynamics from Gen Chem. You should look at that on your own. We actually covered it earlier this semester where they just talk about enthalpy and entropy. And so I just wanted to let you know that. Because we're now going to move on to a new functional group, technically. And this one is the epoxide. And so first you need to know how to name it. Okay, so we're going to learn the nomenclature for epoxides. It's really, really simple. Okay. Not epoxies. Epoxides. Okay, so the nomenclature for epoxides. What does an epoxide look like?
It's a triangle with an oxygen.
Right, it kind of has this generic, look, and then things can be hanging off of the other two vertices of the triangle, so to speak. Okay, it's very, very simple. You would name the IUPAC name just like you would anything else, like as an alkane, but you just treat the epoxide as a functional group, and it gets the epoxy prefix. So all you have to do is add epoxy prefix. Don't forget the numbers for the locant, and this time you have to add both, because usually the epoxide is 2 contiguous carbons, but it can be a 2-4. Like there could be where it's not a triangle, it's a square. Okay, and so that's why you actually do have to give both numbers. And so like 1, 2, or 2, 3, 3, 4, things like that. Okay, so don't forget the locants. And then, of course, as with everything, make sure that it's in alphabetical order. So alphabetize. Okay, so let's just do an example or two. There we go. Now give everybody a moment to get caught up while I take a swig on my Diet Mountain Dew. So today's lecture is brought to you by Diet Mountain Dew. I bet the university would love it if I could somehow, generate them funds with Diet Mountain Dew. Okay. So what will be the root? If this was just an alkane, what would be the root here? Pent, and the ending would be ane, so it's a pentane. So that's still the same. What else would it be? There's a fluoro group. So we've got a fluoro group. Here, this would be called a methyl, and then this is going to be called epoxy. And then don't forget the one other thing that, for whatever reason, people often forget, cyclo. So this is a cyclopentane. That's going to be so we got a cyclopentane. But now we have to add, well, this let me add, oh good. We have to add all the extra stuff there. So now we have to do numbers. Okay, what do you suppose on that was going to get priority? The F, the methyl, or the epoxy? The epoxy, okay? And so which one is going to come first in alphabetical order? Epoxy, fluoro, or methyl? Epoxy. And so let's give it its locant. It's 1, 2, epoxy. Then a slash. Then which comes next? Fluoro or methyl? Fluoro. Now, what number would the fluoro be? And actually, I have to look on somebody's notes. Make sure, what do you think? 3. Okay. 3 fluoro. And what number will the, last but not least, the methyl be? 5 methyl. And of course, if we would have had 2 or something like that, then there would be a dye and all that kind of stuff. Okay. Let's see. Oh, there's no space. Don't replace it. There we go. Except for whatever reason, it won't let me put it all in one line, but that's okay. It's 1, 2 epoxy, 3 fluoro, 5 methyl cyclopentane. That's a mouthful. All right. So now we're going to do the next reaction. And I do want you to know this mechanism because it is a beautiful mechanism. It's unlike anything that we've seen so far. So it's called the epoxidation of alkenes. Isn't it? It's a beauty. You'll see the reason why. Because technically it's just one step. So it's the rate limiting step is going to be the one and only step. And so it's called epoxidation. Whoops, misspelled it. Epoxidation of alkenes. So what do you suppose we're going to be starting off with? An alkene. What do you suppose that we're going to end up with? An epoxy. So, yeah, really difficult. And we lost it. All right, so we have our generic alkane. This is not the mechanism. This is just the generic reaction. And it takes a new player, and it's technically a new functional group that you haven't seen before. We're going to see it like one other time next semester, but it's called a peroxy acid. It's very, very similar to a carboxylic acid. And so, carboxylic acid would have an R, an acyl group, and then what else would it have? OH. Well, a peroxy acid actually has OOH. It's got an extra, because a peroxide technically are 2 oxygens that are single bound to each other. So this is a peroxy acid. And the very last oxygen is the one that's going to be incorporated as the epoxide. Okay, so that's why I've got that as a little line. Then you're going to end up forming, once again, that's called a peroxy acid. You actually get 2 organic products out of this. One is our epoxide. And then the other is a carboxylic acid. And so technically this would also, at this point in time, would be a way for you to make a carboxylic acid. It's not the most efficient way to make a carboxylic acid, but if I ask you to propose a synthesis of a carboxylic acid, now you will know one way to do it. Okay. And as I mentioned, the mechanism, it's a single bimolecular step. Okay, so what does bimolecular mean? The bi means 2, molecular means molecules, and the 2 molecules that are involved is the peroxy acid and the alkene, so that's why it's pretty simple in that sense. The mechanism itself is not necessarily simple. That's why some people, it's still a beautiful dance. I had a professor at University of Michigan Medical School that would always call that trying to make science sexy. So, okay. So we have, I'm just going to use the simplest of the proxy acids, or one that only has 2 carbons, just so that way I don't have to draw as much stuff out. But you could have something that was more complex. And I'm going to draw it kind of odd looking, just to make the drawing the mechanism a little easier. Right. And then we have our alkene. Okay. It doesn't really matter so much where we start, but let's start at something that's electron rich. What's one? There are a lot of electrons here. What's one thing that's electron rich? The oxygen, okay, the terminal oxygen. Okay, let's start there then. We have these 2 electrons that's right here. Okay, this is a proxy acid. When we see acids, what do? We protonate. So that hydrogen is going to be leaving, going somewhere. But it's the 2 electrons that had been holding it in place are going to swing down and attack one of the carbons of the alkene. It does not matter which carbon because it's going to be an epoxide. So it's going to form a little triangle here. But we can't leave that alone because otherwise the carbon that got attacked would have 10 electrons around it. So something has to give. What do you suppose can give? The double bond. So now what happens is the other carbon is the one that holds on to the electrons, but those electrons go out and they're going to swing and attack the oxygen that's going to form the epoxide. So that's how we get the epoxide part. Now we just have to show how we get the carboxylic acid. Because we can't leave this alone, because otherwise the oxygen will have too many electrons around it, the one that's being attacked. And so the 2 electrons between the 2 oxygens that are singly bound, that's really reactive. That's why peroxides are reactive. And so what happens here is this bond breaks to form a new double bond between this oxygen and that carbon. Okay, we can't leave that carbon alone because now it would have 10 electrons around it. So something has to give. What do you suppose is going to be breaking or giving right there? The double bond. And so finally, this double bond swings out, so it breaks from the carbon to swing out and take the acidic hydrogen. And this all happens at the same time. That's why I said it doesn't really matter. So it's kind of like a box step. That's why it's kind of like a dance. Your book does a really good job of trying to show the transition state. And usually I try to draw it, but I'm not very good at drawing it. But that's the one and only step. So now let's just draw what's left. So we have the methyl group. Nothing changed with the methyl group. We're going to have a carbon, and I'm going to draw it kind of funky, but it's still a carboxylic acid. It's just drawn like upside down from the way that you normally are used to seeing it, but it's the same thing. And by the way, that right there is acetic acid, which is what vinegar is. And then we have our epoxide. H3CC, yes, because it's the 2 carbons that are bound to each other. Okay. And so that's it. That's epoxidation. All right, I want you to know that mechanism, but there's a couple of important reactions that I want you to know the reaction conditions, similar to the way with hydrogenation, because they're going to be important tools in your organic chemistry tool belt. And what I suggest that you do, and I used to even hand out a sheet of paper that had like suggestions on how to try to organize like all the different reactions. So don't just sit there and memorize everything, but try to learn the logic behind it, especially for like electrophilic addition. If you look back at the way to make an alcohol and the way to make an alkyl halide, the electron pushing is identical. It's just a little bit different on the reaction conditions. This one's a whole different ball game, but yeah, I used to have, and I called it like the organic chemistry tool belt, but then no one ever used it, so I stopped handing it out. But I do suggest that you don't just try to sit down and memorize, because the fact is there's going to be so many by the end of Organic Chem 1 and 2 that there's just no way, unless you have an eidetic memory, photographic memory, then you're not going to be able to do well. Okay, but this next one is called the ozonolysis of alkenes. And the reason why it's important is it's a way to go from an alkene to make aldehydes or ketones. Okay. Oops. So it's ozonolysis. So what does that sound a lot like? And that is correct. Even Apple thinks it's going to be ozone. Ozonolysis of alkenes. And this does utilize ozone. What does lysis mean? Does anyone know? And that's what we're going to be doing. We're going to be breaking apart ozone. Okay, what is ozone? What's its chemical formula? It is not O2. It's O3. All right, so it looks something like, that's ozone, which, looks something akin to this really weird formation. Let's see, 1, 2, 3, 4, 5, 6. And so we have one side that's negative, the middle is positive, and of course there's going to be resonance between the two. But that's neither here nor there. Once again, I just want you to know the reaction conditions. This is actually a two-step process. And so this is the way that many times it gets written. We have our generic alkene, and this time I'm going to write it this way. R prime, R double prime, and R triple prime. These R's could be carbons, they could be hydrogens. There's a reason why I'm going to say I'm doing it this way. A lot of times they write these kind of reactions this way. It'll say like a 1, and it'll have like ozone. And then the second step requires water, and then zinc. So this is just like the hydrogenation required platinum, palladium, nickel, or rhodium. For ozonolysis, it requires zinc as a catalyst. Okay, and so I just want you to know what the reactant is, the conditions, and predict the products. And this is really simple on the way to predict the products. What you do is you look at this alkene, and you just imagine, you can be violent now in your mind, work out some frustrations. Imagine that you're going to take either a guillotine, or you can do a karate chop, it doesn't matter to me, but you slice completely down, boom, right down that double bond. Okay, so we've cut the double bond in two. So now we're going to have two different compounds. The compound that I have drawn on the left is going to look like this. And it's going to have one of the, cannot get this to work, one of the oxygens from the ozone. And then the other compound is going to be the stuff on the right. That's supposed to be a triple prime. I think I kind of ran out of room though. And it's also got the acyl. It's been acylated. And that's it. So that's why if the R's are hydrogens, then you're going to come up with an aldehyde. If the R's are carbons, then you can come up with a ketone. So this is just a handy-dandy tool to have in your organic chemistry tool belt in order to synthesize aldehydes or ketones. Because we know how to make an alkene. You can start with an alcohol or an alkyl halide, dehydrohalogenate or dehydrate that to make an alkene. Then you go from the alkene now to an aldehyde or a ketone. I'm going to scroll this up just so that way we can see an example, a specific example. Whoops, I was doing the wrong order. That wouldn't work. That'd be minus half a point. It's ozone. 2 is zinc and water. Okay, so I'll give you a moment to get caught up and then to predict what the product or products are. At this point in time, I would not expect you to know how to name them. Come next semester, you'll learn how to name aldehydes and ketones. Okay. All right. So what's going to be, I would expect you to recognize the functional group. What functional group or groups have we made in the products? Okay, but I mean, in particular, what one have we made? So you just, once again, you're going to karate chop? That's right, we made a ketone. By the way, that's acetone. And we've made, what else? I'm going to do it in a different color so we can see it better. An aldehyde. Because it has a... And this is acetaldehyde, which is toxic. Acetaldehyde, by the way, is which please don't, if you go out drinking, it's how your body gets rid of alcohol. It turns it first into acetaldehyde and then eventually to acetic acid. And it's actually what causes the toxic effects of alcohol in your body. Okay. And so that's one way that we have to make ketones and aldehydes. And one more is called hydroboration oxidation of alkenes. And you do not need to know this mechanism either, but it's similar to ozonolysis, where I just want you to know or recognize the reaction conditions and predict the products, or know how to go backwards, like what did you start off with to make it. Okay, and so I'll spell that all out. Boron, which we haven't used in the past. So it's hydroboration oxidation of alkenes. What happens whenever we do an oxidation reaction? From Gen Chem. Right, you're losing electrons. Okay, so here, once again, we just have a generic alkene. And there's actually two different ways to do this. This is also a two-step process, and so that's why I'm going to draw it really big. You can, for the first step, they'll either use this hydrogenated boron, H3B, in tetrahydrofuran, that's the solvent, or they will use B2H6 in diglyme as a solvent, which I ran out of room. And the B2H6 is more stable. That's one reason why they would use that one. And then step number 2 is actually that it requires hydrogen peroxide, H2O2, and basic conditions, so a hydroxide, like NaOH, KOH. The reason why that you want to do this, what you're going to find out, it's not a cheating way, but an easy way to see if a carbon has been oxidized or reduced is anytime you increase the number of carbon to oxygen bonds, you're oxidizing. Anytime you increase the number of carbon to hydrogen bonds, you're reducing. And so we actually oxidize this alkene because you're going to end up with this. And now the stereochemistry is important because this is always a cis addition. So that's one of the reasons why we haven't done stereochemistry yet, but this is a way to make a stereospecific alcohol. And so what the product is going to be will look like this. So now I'm going to actually put in stereochemistry. But it's always a cis addition, which cis meant, what did cis mean? Same side. And so that's going to be your product. You're always going to get an alcohol, but it's going to be a cis addition versus you have the anti or trans addition. Okay. So this is just another way later on to have in your handy dandy organic chemistry tool belt. There's only 2 other mechanisms I want you to know. They're both quite simple. But just in case I forget or we ran out of time, it's halogenation of alkenes, which what do you suppose that we're going to be doing to the alkene then if it's halogenation? We're going to add halogens like Br2 or Cl2. And then we also have what's called formation of a halohydrin, which sounds really cool. But a halohydrin is whenever you add both an alcohol and a alkyl halide to a alkene. And so it's a little bit different, but you're going to find out that the mechanism for those two are very, very similar. So, and then this is all coming together because we're going to do what's called retrograde synthesis, which is something that's probably one of the most important parts of organic chemistry, and it's where you always go backwards and you figure out ways. So this is where the logic really comes in. You figure out ways to make compounds from various starting compounds. You always want to work backwards. Okay, and so that's why we're learning all these new tools to put them all together in order to do synthesis reactions. So some people really excel at this and love it, or at least like it. Some people really struggle with it because there's more than one right answer oftentimes. Okay, and so it's not necessarily cut and dried. So not everything is black and white when it comes to the synthesis questions. Okay, so I'm going to go ahead and end class with